So for lesson 72, we are going to look at the continuous, discontinuous, as well as the discrete functions. So three main types that we can be dealing with. So if you want to for your notes, the first main type is called the continuous function. And it gets its name from really the graph of what it creates. If you think of continuous, a continuous ride, a continuous commute.
Do you need anything from me before I leave?
No.
Okay. And then the lessons will be online, right?
Yep.
Okay.
Also the video.
All right, thank you.
Yep. So the first one again is continuous. And if you think of continuous, I always think of something that doesn't stop or goes on forever. And really that's what we're doing here. If we look at our linear equation, I can take my pen, start on the far left, and continue all the way to the right with ever having to pick up my pen. Hence it's continuous. The second example that they give us is a parabola. Starts all the way to the left, and while it has a curve to it, that doesn't matter. What matters is the fact that I can draw the entire graph without ever having to pick up my pencil or pen. So that's why we call it a continuous function. Discontinuous is just the opposite. When we look at these graphs, no longer can we create the entire graph without picking up our pencil. Notice I can draw the left side of this graph right here, but in order to draw the second half of it, I have to pick up my pencil and draw the second one. So it's broken up. I had to pick up my pencil. The second example that they give us for a discontinuous function is called the step function. I think you can see why. But for each one of these lines, I have to pick up my pencil. And as soon as I have to pick up my pencil once, that's enough to say that it's discontinuous. So 2 examples of that one. The third type of function is called a discrete function. And really the only thing you need to know about a discrete function is really it's a set of ordered pairs is what it is. If we look at the graph on the left, very random. There's no structure to this thing whatsoever. We just have dots that are spread out everywhere. And it's just points, therefore it's discrete. The graph on the right does represent a representation or a relation. We have dots that are going diagonally from top left to the bottom right. So it looks like they're going to form a straight line for us. But again, although it forms a straight line, it's just points. Therefore, it's discrete. So when you hear discrete, think ordered pairs. It is just points. So we're going to graph some of these functions, and then we're going to state the domain as well as the range. For part A, they're telling us it's a discrete function. Here are the ordered pairs that we have. We have 2, 3, 4, 5, 6, 7, and -1, 0. And again, it appears that these points form a line, but again, it doesn't matter whether it forms a line or not. The fact is they're just points. That's why it's discrete. If we look at the domain, I think we can state this. 2, 4, 6, and -1. Range R-wise 3, 5, 7, and 0. If we look at the continuous function, g of x is equal to x plus 2. This is our linear equation. Y-intercept is 2. Slope off of it is 1. So up 1 over 1. And we talked about this at the beginning of class, but what would the domain be? All reals. Again, domain are the x's. Well, does it go on forever to the left? Yes. Does it go on forever to the right? Yes. So domain, this is what you need to write, all reals. If we look at the range are the y's, so vertically. Does it go down forever? Yes. Does it go up forever? Yes. Therefore, all reals. For example 2, here they actually want us to determine whether each graph is continuous, discontinuous, or discrete. And if it is going to be discontinuous, then we want to name the x values that make it where the discontinuity occurs. Example A, continuous, discontinuous, or discrete? Continuous. If we look at B, continuous, discontinuous, or discrete? Yeah, some of us are leaning between continuous and discontinuous, and then we see this bubble here. And what that bubble represents is a hole. We have a gap within our function. Okay, so if I'm going to trace this thing, I can trace it up to there, but now I need to pick up my pencil to draw the second half. Therefore, I've broken the rule. Now it's discontinuous. Be leery of that hole or that gap because they love to do that to you. Okay, they try to hide it in there. Since it's discontinuous, we need to identify the point of discontinuity. So they're asking you to identify, well, where's the break in the function? Where does it go wrong? Well, it looks like it goes wrong where the x value is 3. Point of discontinuity, so P of D, point of discontinuity is when that x value is 3. And if we look at C, what one would that be? Discrete. So I'm going to give you a head start. Again, continuous, discontinuous, or discrete. Determine whether or not it is a function. And then you need to determine the range as well as the domain. Go ahead and just start with A.
So do I have a question?
Yeah.
So for example 2, example 2, the B, could you do what's it called? The point of discontinuity, in an ordered pair? So
Yeah.
3, 2.
You could do that too. You can either give me x is equal to 3 or like the book gives you the point 3, 2. Either way. Let's go ahead and begin by identifying continuous, discontinuous, or discrete. Gavin, which one of the 3?
Discontinuous.
Mm-hmm. Very good. Now it's not asking for the point of discontinuity, but if we wanted to identify it, what would it be? Okay, 2, 3. You can write it as an ordered pair if you want to, as well as 5, 3. Function or not a function? What do we use when it comes to a graph to determine whether it's a function or not? vertical line test. So yeah, we are tempted to say no, not a function because we have these holes, but according to the vertical line test, it still passes it. So it is a function. Even though we have holes and gaps, it's still a function. Lastly, domain and range. You know, does this thing go on forever to the left? Yes. Okay, it's going down, but it's going to the left as well. Does it go to the right? Yes. So we are tempted to say that the domain is all reals. The only problem is these 2 points of discontinuity. So we want all of the x's are all reals except when the x is 2 and 5. Because apparently when we plug in 2 and 5, something bad happens to our function. More than likely we get it to be undefined. So we cannot use those two. If we identify the range, does this thing go down forever? Yes. Does it go up forever? No. Where does it stop at? That's the key. Well, it stops when your y value is 3, am I right? So here's all you have to write. I want all the y values that are less than or equal to that 3. If I look at a y value at 3 or below, I have a graph. As soon as I go above 3, I don't. Let's try another one. B. I want you to identify continuous, discontinuous, or discrete, function or not a function, domain and range. Let's start with our 3 types. Which one of the 3 is it? Continuous. Function or not a function? Function passes the vertical line test. At most one place, so we're good there. Let's go to domain. What type of x's are we looking at here? Does it go on forever to the left? Yes. It's climbing very quickly, but this thing, if we continue to zoom out, will continue to go to the left. Same thing to the right. Therefore, our domain is all reals. How about our range?
Y is greater than or equal to 0.
Bingo. It does not go down forever, but it goes up forever. Where's that stopping point? Well, at 0. Therefore, we have all the y's that are greater than or equal to 0. Catching on? Let's do one more. The obvious one, what is this one? Discrete. Function or not a function?
Function.
Yeah, it is a function. You know, we don't typically think it is with points, but vertical line test tells us at most one place. Even if I draw in a vertical line here, it doesn't intersect anywhere, but again, at most one. So it is a function. How about the domain?
-3, 0, 2, and 4.
Again, domain are our x's. Where do we have some x's at? Well, I have an x there at -3, 0, 2, and 4. Where are my y's at? 3? Any others? Nope. Because they're all 3.